Good morning, everybody. My name is Hassan Salam. I work for Alexandria University, and today I'm going to talk to you about the evaluation of ovarian function. Now, there are two ways of evaluating the ovarian function. There are direct ways and there are indirect ways. The direct ways, direct methods, is that we go directly, we measure the hormone in the blood. The hormone, of course, can also be present in saliva, or we measure the metabolites of the hormone in the urine. The other way is to look by ultrasound at the ovary to see, to scan the follicles and see if there is any activity in the ovary. The other methods of evaluation are the indirect methods. So we measure the effects of the ovarian hormones on different organs or target organs or tissues. Like, for example, vaginal cytology, cervical mucus changes, endometrial changes, ultrasound scanning of the endometrium, not of the follicles, but of the endometrium, and measuring the basal body temperature, and there are other changes also. So let's remind ourselves of the hormones which are secreted by the ovary, mainly the estrogens and progesterone. And when I say estrogens, I really mean estradiol 17 beta, which you can see the formula is present down there, together with the metabolite, which is estradiol 17 beta glucuronide. This is the main metabolite. And as you can see in the red circle, this is a glucose molecule which is attached to the estradiol at the 17 beta position. Therefore, this molecule is the estradiol 17 beta glucuronide. Now, estradiol is a small molecule. As we said, all estrogens are 18 carbon atoms. Its molecular weight is 272. Most of it is carried by a protein called the sex hormone binding globulin. But it is the free part, which is the active part. It is the free part which goes inside the cells and attaches itself to the receptor and then does the function of the hormone, while the others which are bound to this protein are not the active ones. We may remember here that all the estradiol present in saliva is free. There is no sex hormone binding globulin in the saliva. So if you want to measure the free fraction, either that you measure it in the blood, but you have to do what we call a separation step. You separate the bound from the free, or you go to the saliva and measure it in the saliva. Of course, the level in the saliva is going to be much lower, so the test is going to be more sensitive. And as I said, we can also measure the metabolite of estradiol in urine, which is mainly estradiol 17 beta glucuronide. The other hormone, of course, is progesterone. And we remember that progesterone is 21 carbon atom. When it's an O, it means that you have a double bond O. And again, it is, as you can see, the chemical structure below at the bottom of the slide. But on the right bottom side, you see also the progesterone attached to a molecule of glucuronide. So this is pregandiol 3-alpha glucuronide, which is the metabolite of progesterone. So we either measure progesterone in the blood or pregandiol 3-alpha glucuronide in urine. And again, 20 to 40% of this progesterone is carried by another protein, the corticosteroid binding globulin. So this globulin carries two things actually. It carries the cortisol and it carries also progesterone. And again, it is the free fraction, which is the active fraction, and which is also present in saliva. Saliva, we only have the free fraction. And as we said, the metabolite is 3-alpha glucuronide. So how are we going to measure these hormones directly in the blood of the patient? Now, there are three groups of hormones. They are classified like this historically. Scientists started by using biological assays to measure hormones. After that, they started to use physico-chemical assays. And finally, since the late 1960s, they started using the binding assays. So what's the difference? The biological assays, they measure the biological property of the hormone. For example, we know estrogens can, or estradiol, if injected in the mouse, it will do some changes in the vaginal smear of the mouse, the wall of the vagina. So the doctor will inject the urine of the patient and do a vaginal smear for the mouse and see if the response in the vaginal wall is denotes the presence of estrogen. Another example is the cropped sac test for prolactin. Now, cropped sac in pigeons is like the breast in women. So again, we inject the urine of the patient and then we weigh the crop sac. We weigh it before and we weigh it after. Of course, we have to sacrifice the pigeon for that. Now again, the tests is very crude. These biological assays are very crude. They can only measure the lower detection limit, what we call sensitivity of the test, can only be in milligrams. So that's 1 gram divided by 1,000. So they're milligrams, really. And they're very crude, therefore they cannot differentiate, for example, between estradiol and estriol. It's all estrogens. But there is a principle that we have to remember here. When we do any assay, we really have to do what is called the dose-response curve, sometimes called the standard curve. Say, I want to measure progesterone. So, before measuring the unknown samples I do a standard curve. I have samples which contain progesterone, and I know exactly the amount of progesterone in these tubes. One of them, for example, contains 50 nanograms, the other 25, the third one 12 and a half, the fourth one 60.25. So I do the experiment on these 4 or 5 points, and then I plot the curve. Then when I do my samples, the unknown samples, by the same way, I can plot the response on the curve. Therefore, this can give me the result, the level of the hormone. So this principle has to be remembered because it is used for any hormonal assay. After the biological assays came the physico-chemical assays. And these assays measure a physico-chemical property of the analyte, the hormone. Meaning what? As you can see in the lower panel, for example, all the 3 estrogens we know, estriol, estradiol, estrone, have an 18 carbon atom. They also have an aromatic ring, A-ring. So what Dr. Brown from Australia did is that he came up with a method where he would add the Ittrich reagent and then the Cooper reagent, and then this results in a color, and then he measures this color with spectrophotometer. So this was the Brown method for measuring estrogens in urine, because as you can see, you cannot differentiate really between estriol and estradiol and estrone. They are all together in the same test. It is less crude than the biological assays, but still cannot differentiate between estradiol, estriol, and estradiol, and therefore also the sensitivity is better than the milligram range. Now it goes to the microgram range, which is 1,000 times less than the microgram. Because this is something we may need to remember. If you divide the milligram by 1,000, you get a microgram, by 1,000 a nanogram, then a picogram, then a femtogram, then an altogram, a zeptogram, and a yoctogram, as you can see here. But in our hormonal assays, we usually go down to the nanogram and the picogram levels. The third method of hormonal assays, which came after the physico-chemical assays, is the binding assays or the immunoassays. Now, these assays measure the binding properties of the hormone, but they have very good sensitivity. You can go down to the nanogram, which is 1 divided by 10 to the power 9 of a gram, and even to the picogram, 1 divided by 10 to the power 12. Progesterone, for example, is usually in the range of nanograms per milliliter, and estradiol is usually in the range of picogram per milliliters. And these assays, because they depend on the immunological properties of the analyte, of the hormone, they can differentiate between estrone, estradiol, estriol, and so on. And the examples of these are the radioimmunoassays. And let us say how these work. Well, the people who have actually invented this method were Yalow and Pearson. And they studied this method in 1960, but Yalow received the Nobel Prize in 1977 because Pearson had died in 1972, and the Nobel Prize has to be given to somebody who is still living. What they did is the following. They wanted to measure insulin in blood. And at that time, insulin was not produced in the laboratory. It was taken from the pancreas of cows and injected in humans. So some of these humans developed antibodies. So Yalow and Pearson used these antibodies, to measure the insulin in the blood. So they said, if you want to measure insulin, give us an antibody to insulin and give us an insulin which is radioactive. We will add to them, so we will add the three together. So the radioactive insulin will compete with the insulin in the blood of the patient, in the sample, with this limited amount of antibody. And therefore, some of the hormone is going to be bound and some of it is going to be free. Then we separate, then we measure. And let's see the details. See, for example, in tube number 1. This is a sample. And suppose you want to measure progesterone. So these white rounded circles are molecules of progesterone. So you add to them radioactive progesterone. So they mix together, like you see in number 2. And then in number 3, you add the antibody to progesterone. So what happens in number 4 is that the progesterone in the sample and the radioactive progesterone are going to compete with this limited amount of antibody you have added. So some of them are going to be bound and some of them are going to remain free. So as you can see, there are some free progesterone from the sample and some free radioactive progesterone, which did not find any antibody to bind with. So what you do after that is you add something to do the separation. So you add charcoal, for example, because charcoal is going to take the free fraction and separate it. And then you will have, you take the supernatant, which contains some bound progesterone labeled and some bound which is not labeled, and then according to this fraction you can get the results. Now, because of this method, these binding assays have a very low sensitivity, as we said. They can go to nanogram levels and to picogram levels. And they were introduced in medicine in 1960, so by 1970, this diagrams, which we take now for granted, were published in 1970. This is Professor Robert Jaffe from the University of California at San Francisco at the Moffitt Hospital. But that time he was in Missouri. But as you can see, this was introduced in 1970 by this group. But another group did the same thing at the same time in Columbia University in New York City under the chairmanship of Professor Raymond Van der Wiel. And as you can see, the names Bogumil, Darienfos, Ferrin, Ferran, Jeverevich, Warren, but two Egyptians there, Professor Tofir Sgalla and Professor Girgis Mikhail, who became professors themselves in America afterwards. So this diagram could only be done after the discovery of radioimmunoassays. And although these immunoassays started by radioactive radioimmunoassays, because the labeling was done with radioactive material, people started to put this material to get rid of it in the sink. So there was a fear that this would do a lot of pollution. So people started to look for other methods of labeling. So if you label your hormone with fluorescence, you can have a fluorescent immunoassay. With luminescence, you have a luminescence immunoassay. You can even label it with a virus, a phage. So you have a phage immunoassay. You can even label it with an enzyme. So you have the enzyme immunoassay. One variant of it is what we call the ELISA, enzyme-linked immunosorbent assay. And even the metallic ions, which change color when they are bound to the hormone, like the pregnancy test, for example, which is done on a slide. So these are the methods for measuring the hormones in the blood, in the saliva, or even the urine. Now we come to another method of direct evaluation of ovarian function, which is looking at the ovary with ultrasound. So how does ultrasound work? Well, ultrasound waves are produced by passing electricity into in a piezoelectric crystal, which makes it vibrate. Now you pass electricity in the crystal, it vibrates. You bring back vibration to the crystal, it generates electricity. So when this crystal vibrates, it vibrates with a frequency which is higher than the human ear can grasp, more than 16,000 oscillations per second. This is what's called ultrasound. And these waves, which are mechanical waves, they can penetrate the human tissues, and they are reflected at each surface. They are reflected, for example, they pass through the skin, some of it is reflected, the rest goes inside, and then some is reflected at the level of the uterine wall, and then the rest goes inside the uterus and goes reflected from the face of the baby, and then some goes on, and so on. So the ultra waves, which is mechanical waves, they penetrate the human tissues and are reflected differently at each surface depending on their acoustic resistance. And the ultrasound machines, of course, these crystals are placed in the transducer. And what the transducer does is that it fires the electricity, generates ultrasound for 1/100th of a second, and waits for the rest of the second to receive the echo. So it's pulsed ultrasound, really. And the resulting echo, when it hits the crystal back, when these mechanical waves hit the crystal will generate electricity, and electricity is going to be transferred in the picture. So these ultrasound, I should remind you that they are mechanical waves. Therefore, prolonged use of these ultrasound can make the shear forces on the tissues as if you're hitting forces mechanically. But of course, because they are very minute amounts, and they're very minute times, 1/100th of a second, these amounts are safe. And here are the different transducers. At the beginning, the transducer contains more than a crystal. For example, on the left side, the upper left side, the mechanical sector transducer. This transducer, for example, has three elements, has three piezoelectric crystals, and they rotate. So one of them works and the other works after it, and so on, because by doing this, you can generate a real-time ultrasound. You can generate a video rather than a picture. But at the beginning, of course, ultrasound could only generate a picture, but after that, it now generates a video. You can see the fetus while it's moving. So you can move the crystals like this, or you can start firing the crystals in sequence by playing with electricity. So you fire one crystal and then the other and the third and so on, with different sorts of transducers like the phased array sector transducer, linear array transducer, and now most of the machines have a curvilinear array sector transducer. And by doing this, either abdominally or vaginally, we can see the follicles, we can see the small follicles, and then we can follow them until they are about to ovulate, and then they ovulate. And this is the growth of the follicles. We cannot see follicles less than 5 millimeters. As we remember, the follicle which is going to ovulate nowadays has started growing at least 85 days beforehand, according to the work of Goujon in 1996, as you can see here. Therefore, we can only see by ultrasound the follicles which are about 5 millimeters and so on, starting from the beginning of the active cycle we're talking about. So follicular growth can be monitored either by abdominal ultrasound or vaginal ultrasound. And follicles of less than 5 millimeters difficult to see. And mind you, artifacts, cysts, and other structures may resemble follicles. So ultrasound is not God's answer to all problems. We can create pictures with ultrasound. You can see things that does not exist. You can think that this is a follicle and it is not a follicle. So this is something we have always to remember. Because if it is a follicle, it will reach about 18 to 20 millimeters before ovulating. Now enough for the direct methods. Let's look at the indirect methods, which means the measurement of the effects of the ovarian hormones on the different tissues and organs. And let's start by vaginal cytology. This is the wall of the vagina. As you can see, it is at the very bottom, you have the basal cells. And these cells never separate from the epithelium, because above them you have the parabasal cells, then the intermediate cells, then the superficial cells or the squames, seen sideways as you can see, but also seen from above as you can see. And the basal cells have a big nucleus, and the more the cell grows and matures, the nucleus becomes smaller and smaller until at the end it loses the nucleus. So the superficial cells have what we call a pycnotic nucleus, very small nucleus. And as you can see on the left side, estradiol usually pushes things in the way of maturity. So a woman who is under the effect of estradiol will have a large amount of superficial cells, because progesterone does the opposite. It stimulates really the intermediate cells, or it stops the intermediate cells from becoming superficial cells. So what we do is that we take a vaginal smear, not a cervical smear. Cervical smear is meant to look for cancer, for early cancer, but no, we're not talking about cancer here. We're not talking about the cervix here. We're talking about the vaginal wall. We take a swab, a smear from the vaginal wall, we put it on a slide, and we stain it with hematoxylin and eosin, acidic and basophilic stain. And as you can see, the basal cells are blue, with a big nucleus, as we said, the basal and parabasal. The intermediate have a smaller nucleus, and they start to become more or less violet, while the superficial cells or superficial squames have a small nucleus, pycnotic nucleus, and a red cytoplasm. This is how it stains with hematoxin eosin stain. So there are three types of cells which come with us when we do the vaginal smear, because the basal cells do not separate. So as said, if the woman is under estrogen effect, she will have a lot of superficial cells, and progesterone increases the intermediate cells. Now, we have what we call the maturation index. How do we calculate the maturation index? We start by the percentage of parabasal cells, then intermediate cells, then superficial cells, from below upwards. As you can see here, examples. The late follicular phase, say day 12 or 13 of a cycle, the woman is under a strong effect of estradiol, you will find few parabasal, 10%, and 10% intermediate, while 80% of superficial cells. On the other hand, if you're talking about the luteal phase, so the effect of progesterone is to do mid-zonal effect. So you will have 30% parabasal, 40% intermediate cells, and 30% superficial cells. While a woman in the menopause who has no estrogen, no progesterone, will have most of her cells are going to be parabasal cells, 80%, and 10% intermediate and 10% squamous. Pregnancy, of course, is characterized by a very high level of progesterone. So we will have a high mid-zonal effect, as we call it. So the maturation index can be like 20, 60, 20. And the cells usually, these cells, these mid-zonal cells, these intermediate cells, will have folded side walls, making them look like a boat. This is why they are called navicular cells. And this can, in theory, be used as a pregnancy test. If a woman has a delayed cycle and we do a vaginal swab or vaginal smear from the side of the vagina and we find a high mid-zonal, then she's probably pregnant. And this is another example how the things change from the premenopause to the postmenopause. The second group of changes happen in the cervical mucus, in the cervix actually, as we can see here. According to the cycle, at the beginning of the cycle, the cervix is diameter is small, cervical os is small, starts to increase, maximum around the time of ovulation. The quantity of mucus, of course, increases again, reaches the maximum around the time of ovulation, and then diminishes. The ability to make threads, the thread ability, Spinnbarkeit. Spinnen is to spin. Spinnbar is threadable. Spinnbarkeit is threadability, the ability to make threads. As you can see, if you go to a slide and a slide cover and you try to they are separated by the cervical mucus, you can see that you can make a long thread around the time of ovulation. Another thing is arborization, which means that you put the cervical mucus on the slide and leave it to dry in air. And you will find that around the time of ovulation, you have arborization. It looks like the trees, arbre in French. So you have this like, as you can see them under the microscope. This is because of the sodium chloride crystals, which crystallize on the slide. And of course, the famous basal body temperature. So the cervical mucus changes, and the cervix itself changes with the ovarian cycle. And even if you look by MRI, magnetic resonance imaging, you find that around the time of ovulation, this is the estrogenic mucus, the nice, abundant, thin, that makes a long Spinnbarkeit thread, is usually the estrogenic one, day 12. While on the right side, you have the gestational type sac under the effect of progesterone, say during the second part of the cycle, and you see here that the sperm is trying to penetrate and cannot penetrate, while on the left side, as if there are highways for the sperms to penetrate and swim through them. These characteristics have been used by Dr. Billings and his wife to come up with the Billings method for natural and feminine planning and to tell women to examine themselves in order to know roughly their fertile period. So if they don't want to use the pill, they don't want to use the intrauterine device or any other method, they want to go naturally, then they can use this method. But of course, they have to be trained, the woman has to be trained about it, and as you can see, she can examine herself and see if she is in the fertile period or not. The third group of changes are the endometrial changes during the menstrual cycle. And you can see this cycle is divided into the 5 days of menses, then from 5 to 15 the follicular phase, then from 15 to 20 the luteal phase. And during the follicular phase, under the effect of estrogen or estradiol, the endometrium starts to grow and reaches its maximum, reaches a good thickness in the pre-ovulatory period, just before ovulation. And this thickness remains more or less until the next cycle. At the beginning, the glands are straight, while under progesterone, the glands will become more or less tortuous. And at the beginning, under estrogen, the glands are more or less cubical, while the cells lining the glands are cubical, while on the right side, under the effect of progesterone, the cells become more or less columnar. So this is how it is. In the proliferative phase from day 5 to 14, the effect of estradiol is felt. So in the early follicular phase, they say from day 5 to 9, the endometrium is thin, the glands are straight, as we said, the cells are cubical, and then there was no secretory vacuoles inside the cells. In the late proliferative phase, the endometrium is thicker, the glands are straight, the cells become more cubical, are still cubical, and there are no secretory vacuoles still, but only the endometrium becomes thicker. When the luteal phase starts and the progesterone is secreted, now the effect of progesterone starts. In the early luteal phase, the endometrium is still thick, the glands start to become convoluted, the cells become columnar, and the vacuoles appear. At the beginning, they are below the nucleus, say day 15, 16. 17, 18, they are above, they are around the nucleus. Then from 18, 19, they are above the nucleus, about to burst inside the cavity of the gland. Because in the mid and late follicular luteal phase, which is called the secretory phase also, so that's after day 20, you found that endometrium is thick, the glands convoluted and less columnar, but you see that secretions have gone out of the cells and into the glandular space. This is why when before the era of hormonal assays, when we wanted to know if the woman is ovulating or not, we would take a premenstrual endometrial biopsy, send it to laboratory pathology, and they will come back with a report saying secretory, meaning that she has ovulated, or non-secretory means that she has not ovulated. Because this information, but good pathologists have a lot of details, and they can actually use this information to date the endometrium. They can tell you exactly this endometrium is day 18 or day 23 and so on. These details, of course, are beyond our necessity now. The other way of evaluating the ovarian function indirectly is to look at the endometrial changes with ultrasound. And as you can see in panel A, during the follicular phase, the endometrium is thin. And then, around the time of ovulation, you find that the endometrium takes like what we call a triple line. And then, after secretion of progesterone, the endometrium becomes a homogeneous shadow. Again, we have the basal body temperature. We know that after ovulation, the basal temperature starts to rise. It is not a fever. It is just half a degree or less than half a degree actually change. So why is that? Because progesterone is a thermogenic hormone. If you inject it into a man, it will raise his temperature. Body temperature shows a slight rise after ovulation. It's not fever. It was 37 minus 0.2. It now is 37.1, for example. So it's a very small amount of heat. Can increase in some people more than that. But if a woman wants to follow her temperature chart, she should take her temperature when she is still in bed before rising, before doing any activity actually, because this will show we are looking for very mild changes in the temperature. And as I said, the best time for doing this for becoming pregnant is to have intercourse on the day before the rise. So people will always have the information retrospectively. Because finally, we have other changes also during the menstrual cycle or during the ovarian cycle. Everything in the body of the woman changes. For example, the cervical mucus chemical constituents. If you look at cervical mucus enzymes, and people have studied this, or glucose, or chloride ion. If you look at vaginal organic acids, or the breast temperature and volume, or the vaginal blood flow, all these things change during the ovarian cycle. And with this, I come to the end of my presentation, and I would like to thank you very much for your attention.